Now, the very first thing we've done is time a ball running down a ramp, do the number of counts, your own count. Just make it an even count. So you release the ball, so you sort of go 1, 2, 3, release, 1, 2, 3, 4. Kind of a little faster, a little slower, it's up to you. Okay, so let's just say that you determined that the ball moved 56 centimeters from your first count to your seventh count. Then, what can you determine from that? Well, first thing you can easily determine, if you know how far something goes and how long it takes, is how fast it's moving. Now, we calculate what we're going to call average velocity. There's a difference between speed and velocity, but we'll get to that distinction very shortly. Okay, or we have actually gotten to, because this is a little later than this was actually, it's been several days since this class. Okay, anyhow, to calculate the average velocity, we just divide the 56 centimeters by the 7 counts, and we find that we went 8 centimeters per count. Now, usually this won't come out a whole number, but to keep the calculation simple, I fudged a little bit, although 56 centimeters is a pretty realistic distance on that 60 centimeter ramp. You don't want to release it from the very end, and the ball has some diameter and stuff like that. So, so that works out. But okay, so we have this. Now, my question is, can you make a velocity versus time graph for something that starts from rest and takes 7 counts to go 56 centimeters? First thing I asked was, what's your velocity versus time graph look like? Does it look like this, 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 this? What could it possibly look like? And we had some discussion of that. And most people drew either a straight line or a line curving up or line curving down. And any of those is actually a pretty good conjecture. If you're moving on a straight ramp, it turns out that if you ignore a couple of very secondary effects, the fact that friction varies with velocity and stuff, you should get a straight line graph. And of course, if the velocity starts at 0, the graph should start at 0. Now, it also ends, okay, because the ball doesn't keep moving past the end of the ramp, presumably, or if it does, the nature of the graph changes. So we only graph the section of the plane, the section of the straight line that actually corresponds to motion on the ramp. And it turns out that it should be like this. Now, there are other possible graphs, okay? I started this one at the origin. Well, of course, that's implicit and made it very explicit. On a V versus T graph, the velocity has to start at 0, the velocity on that ramp, to mimic the condition we have here. Now, the velocity doesn't always start from 0, but in this case it did. So when you draw this graph, the velocity has to start from 0. There's no reason the time has to start from 0. Okay? Even with your count, you could have started. You could have started the ball on a count of 8, okay, and counted to 15. Then you would say, well, there were 7 counts from start to rest, but it didn't start at 0, it started at 8. So a graph that looks like this would be also perfectly valid. Okay? Now, this graph or this graph might be valid if you have a curved ramp, curved one way or the other. It could well be that you have a velocity versus time graph that looks like this. Certainly you're not going to have one that looks like this, because for this time you have 1, 2, 3 velocities. You can't have 3 different velocities at the same time. Okay? You can have many different velocities over the motion down the ramp, but at one specific time you need one specific velocity. So you can't violate this vertical line test, meaning that, of course, your velocity is a function of time. And make sure you understand your pre-calculus well enough to understand what I just said. And what's the vertical line test? How does that ensure that you have a function? What is a function? Make sure you understand those ideas. Another graph that somebody could actually get, let's say you're counting Start 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, to keep a steady rhythm. Okay, that would be a reasonable way to count, and that's kind of the way I instructed you to count. Well, the velocity from 1 to 4 goes up, okay, and then you start over at 1. And your velocity here is equal to your velocity here, but then the velocity keeps going up. Okay, well, that would have your count here and your velocity here, but your count wouldn't really represent a running clock, would it? So you want your count to represent a running clock. Even if you're counting, start 1, 2, 3, 4, 1, 2, 3. Okay, well, that's 7 counts. But you represent that 1, 2, 3 that follows the 1, 2, 3, 4. On the graph, that'd be 5, 6, 7, right? Okay, well, those are just minor points and things that are pretty much common sense. Okay, now we construct a graph, and of course we constructed this more slowly and in more detail. But if we go ahead and start the graph at t equals 0, it will extend up to some point, and that point will be at count 7. And that point will be across from some velocity. But our average velocity on a linear graph will occur at the midpoint of the interval of the graph, okay? The interval of the graph on the domain of the motion, okay? So the midpoint of the graph is here, and the midpoint time will certainly be here. If this is the midpoint of this segment, this will be the what we call the midpoint time, and that's going to be halfway between here and here. Well, this is 0, this is 7, that's going to be 3.5 counts. And that's where our average velocity will be. So here's where our average velocity is. So we calculate this average velocity, and that's going to be the velocity at the midpoint of this section, of this segment. And the time is going to be 3.5 counts, and the velocity is going to be 8 centimeters per count. And it never did put the units of the velocity here. If I don't put the units up here, I have to put the units on these numbers down here. Now, common sense. What's the velocity going to be here? Well, this point cuts the segment in half. This triangle, therefore, is similar to this triangle, geometrically similar, because these legs are the same and the slope is the same, so the rise has to be the same in both cases. So you have a rise from here to here of 8 centimeters per count and a rise from here to here of 8 centimeters per count. That gives you a total rise from here to here of 16 centimeters per count, meaning that your final velocity would be 16 centimeters per count, double your average velocity. And as it turns out, anytime you have a graph that looks like this, the final velocity will be double your average velocity since you're starting from 0. But if you don't start from 0, that's not true anymore. So you don't want to get used to just doubling your average velocity. If you do, I almost guarantee you, you're going to double it sometime when your initial velocity is 0. And if it's on a test, I'm not going to be very sympathetic. And, I might feel badly that you did that, but you're not going to get any points that you wouldn't otherwise lose. Okay, that didn't make any sense, but you can fix it. Okay, now, that's all a very simple picture, and you need to master that picture right here on the first day, right here as soon as you see it. Well, before the next class. Now, the next class has already occurred, and one more after that, and some people are still not understanding this picture. So take a lesson here that you need to understand one class by the time you come to the next, and you need to get your work done by the time you get to the next class. You get in a downward spiral, it just doesn't work if you do otherwise. Because everything builds. You don't want to be struggling with ideas from the last class in the next class. if at all possible. Now, some ideas are tough, and that's going to happen, but, I would hope that everybody would focus on this and completely understand this idea. Okay, well, there's a calculus connection here. Average velocity, the average of any function. Average velocity is represented by v bar as well as by vf. Okay, I can't type a v bar, I can type a vf. And since I type a lot of stuff, I can't use this notation, at least not easily. The average value of any function on an interval from, say, a to b is the integral of that function from a to b divided by the length of that interval, b minus a. In this case, the average velocity for this velocity function would be the integral of the velocity function, the v of t function, whose graph is a straight line of, with the slope of this line. And we haven't talked about the slope yet, but that's pretty straightforward. The interval, if you integrate that function from here to here, that would be from t equals 0 to t equals 7 counts. Then b minus a is 7 counts minus 0 counts, or 7 counts. That's how long the interval lasts. That's the duration of the interval, or in general, you consider that the length of the interval over which you're integrating. So if you integrate v of t from 0 to 7 counts, whatever the v of t function is, and divide by this, you're going to get the average velocity, and you would get 8 centimeters per count if you have the right velocity function. Okay, now, final velocity, as we've seen, is 16 centimeters per count. The slope is rise divided by run, and that's very easy to calculate. We could use any 2 points on this straight line, because the slope is the same everywhere in a straight line, and calculate the slope. So we could calculate it between this point and this point. The rise would be what? From here to here, the rise is 16 centimeters per count, and the run is 7 counts. So the slope of this graph could be then 16 centimeters per count over 7 counts, which is 16/7 centimeter per count And that comes out centimeters per count squared if you just do the fractions. Okay. Now I was going to comment on this. The premise up here isn't clear the way it's written out. So the thing I'll say about this is, from this, that we'll talk about later in more detail because I didn't write out much about it, v is at plus c. V is a linear function of t. And that comes from the premise that dv dt is constant and equal to a. If dv dt, the derivative of v with respect to t, is a, of course that means the slope of the v versus t graph is a, because the derivative represents the slope. So if we integrate both sides of this, if we integrate dv dt, we get v. If we integrate a with respect to t, we get at plus c. And it would follow then that v is a linear function of t with a slope of a and a y-intercept of c, whatever that happens to be. And that would give us the equation of this straight line. Slope would be 16/7 centimeters per count, and c would be the y-intercept, or the vertical intercept. I shouldn't actually call it the y-intercept, which is 0. So you'd immediately have a velocity as a function of time. But we talk more about that in subsequent classes or later in this class. So we'll pick that up when the time comes.